Hi, it's so cool to be here. This is my first trip to Australia. It's fantastic. And yeah, my name's Liz. I work for Aqua. If you want to talk about security, then myself and my colleagues, Eric and Erez, are out in the sort of exhibition area, and we can talk about security as much as we like, but that's not what I'm going to do now. I'm going to talk about what containers are. It's called the sequel for a couple of reasons. So I have spoken at Container Camp before and done this presentation around how you can build your own container in a few lines of Go. And I promised Angie that I would add to that. It wouldn't just be the same talk. So there's some new aspects in this talk. I think it also turns out the timing is quite nice that it follows on from Vishnu's talk this morning, because I think it explores some of the same concepts around what containers really are, but through a different lens. So it's the sequel in a couple of different ways. So we're going to cover a few things, and I know we're all keen to get to lunch, so I'm just going to have to race through, build a whole container that does all these things in half an hour. It'll be fine, it'll be fine. So we're going to talk about what namespaces are. I'm going to explore a little bit of rootless containers. Tomorrow, Alexa, who has basically done all the work on rootless containers, will be talking about them in a lot more detail, but I'll just give you a little insight, perhaps a little overview. We will show how C groups work, and then, since I'm working for a security company, it's nice to set off an exploit in my container. Right, so without further ado, we're going to write one in some code. So, first of all, I have this big enough. Shout if you can't see the code. Incidentally, any Go programmers here? Okay, there are a few of you. You have to shout when I inevitably make typos. Everybody else, don't worry too much. I'm sure the concepts, you don't need to worry too much about the exact syntax. I think the concepts will come through. So, what we're going to do, we're going to sort of replicate Docker run command. I invoke my program by saying go run main.go, and then just like Docker run, I'm going to have a run command. I've only got one container here, or I will only have one container here, so I don't have to specify the name of a container image or anything. And then I'm going to pass in a command and some arbitrary arguments to that command. So, the first thing we're going to do is have a look at the first parameter and just check that it is actually run. And if it is, then great, we're going to call run. And if it's not, we will fall over in a big heap and die. Okay. And if it runs, we're going to debug, we're going to print out what it is that we've been asked to run. So that will print out arguments 2 and beyond. That's everything after the run. And then in Go, we have this exec package that lets us set up some command that we're going to start a new process and then run that command inside the new process. We don't actually run it until we hit this run function here. So first of all, we're just going to set it up. And we're going to say we want to run the program specified in argument 2, and it may have some parameters. Okay. So at this point, I have a program that does nothing other than execute a command. There's no containerization yet, but it's a good idea just to check that it works, right? So go run main.go, run. Let's say hello container camp. Okay, so that worked. Wow, we can do hello. Great, do echo. Let's add some containerization. So we can set, I was going to show a slide at this point. I was going to show, yes, namespaces. So we're going to add some containerization by adding some namespaces. Namespaces restrict what the process can see. And there are kind of half a dozen of them. I'm not going to do all of them, but we use syscalls to say to the kernel, when you create this process, I would like you to give it one or more of these namespaces. So we're going to say, please give us sysprop attra. We're going to have some flags when you do clone, which is the bit that actually creates the new process. And we want to clone. We're going to do the fancy new Unix time-sharing system. Sounds really complicated, but Unix time-sharing system is just the host name. So what I've said here is when you start this process, give me an isolation, if you like, around the host name. So I can run this. This time we will run a shell so that we can do things inside it. And if I say the host name is currently the name of my Ubuntu virtual machine, I can change it. It's taken effect inside my container, and I can just check that it hasn't affected the host. So that's good. We've got some isolation. We have started to create a container. But it's pretty hard to tell from this window whether I'm in the container or not, and this is kind of confusing. So what I would like to do is have my the host name set up before I run my bash profile script. I'm going to exit here before I get confused. Okay, so you might think that we could do something like, this must thing, by the way, just catches errors. It's really not production ready. Okay, so you might think that we could do something like set the host name here. And what is it? It's a string of bytes. Okay. But you remember I said that we don't actually create the process until we hit this run function. So if I was to set the host name here, I haven't got my new namespace yet. The namespace only actually gets created when I start the new process. So if I run set host name here, I'm going to affect the host name of the actual host machine. So I'm going to avoid that by basically forking and execing twice. So the first time through, I am going to create my namespaces, and I am going to call into myself. So I'm going to run this program again, which you can do by proc self exe. That is actually a link to this program. And then I need to append. This looks really complicated if you're not a Go programmer, but it's not as, it's like magic invocations just to say I want child followed by everything else, all my arguments. Hopefully I've got all the brackets right. So the first time through, I'm going to call run. I'm going to create this namespace. I'm going to start a function that calls this program again, but instead of run as the first argument, it's going to have child as the first argument. So I can do child here. And I'm going to rename this function, this copy of it, to child. And I don't need to set up the namespaces anymore. I've already done that. Incidentally, I have to wire up these stood in, stood out, stood er. Otherwise, it would be really dull and nothing would happen. You couldn't see anything. But when I'm inside this child function, I'm inside the namespace. I'm starting another process, but I'm doing it inside the namespace we set up the first time around. So if this works, we should see the login come out twice, because we do it twice. And we should see, as we do, that hostname got set up before we ran the bash profile, and we can now tell that we're inside the container, which is great. So the next thing that we want to do is be able to isolate the processes. So at the moment, if I'm inside my container, I can see all of the processes running on the host. And we don't want that. We want to have a namespace for processes. This is called new PID. And I need to quit out the container, run it again. We can see that process ID 1. So that is pretty convincing that we have got a new namespace. We're starting to number process IDs within the container, starting at 1. But if I do PS, it's still showing me all these high-numbered host processes, and I can look at all of the processes on the whole machine still. And that's because it's getting the information from /proc. /proc is a pseudo file system. We're going to talk about pseudo file systems again when we talk about C groups. And they look like ordinary directories and files, but they are a way for the kernel and user space to communicate about things. So the kernel is writing information in here about the running processes, and from user space land, I can look at them. And PS goes here to find out information about running processes. So I need my container to have its own copy of /proc. And to do that, I'm going to give it its own file system. I'm going to chroot into another file system. So if I look in my root directory on the host, I've marked it with VM root. And I also have, conveniently, because I knew that I'd need it, another copy of the Ubuntu file system. This one is marked with a file called container root. And I'm just going to chroot into that. And then we've got a proc here that we can use inside the container. So I can do chroot to that copy of the Ubuntu file system. That would actually leave me in some undefined location. So it's a good idea to explicitly say, change me to the root directory. And quit out this exity. Run the container again. OK. Now, my root directory is the container root. That's kind of what's happening when you with your container image. Your container image, it takes a copy, and I'm not even going to go into that whole the file system layering thing, but the result of it is it looks like this. It looks like you have your own copy of, you have your own root, and it looks like the file system of whatever you need inside your container. Right, so can I do PS yet? I can't, but it told me why not, or at least it told me what I can do to make it possible. I just need to mount the proc directory because it's a pseudo file system, and I need to tell it to mount proc at proc, and it's a proc type file system. There we go, that'll do. Enough procs. And I'm going to tidy up after myself and unmount it when I'm finished with it. I think that might work. Right. So this time, yes, PS works. We have a proc directory that is separate and different from what the host can see. If I run a long process inside the container, though, I can see that. Let's do. I can see it here from the host, and it has a process ID of like a high number. So I think that's really an important thing to grasp about containers. They're just processes running inside this isolation layer, but they're still visible from the host. You can still see that process. It's probably ID 11 or 12 or something from the container's point of view, but from the host point of view, it's 2000 or whatever. OK. So that kind of gives us a bit of an idea around how namespaces work and how, there's no, people talk about lightweight VM, but there's nothing, there really isn't anything there. There's no hypervisor at all. It is just Linux processes, but with this different view of the world. So I've been running this as root, and I would like to show the idea of rootless containers. So a rootless container is what you need if you don't have root privileges on the host machine. You want all the benefits of being able to run containers and have all the isolation and dependencies taken care of. But if you don't have root privileges, you can't just install and run Docker. So rootless containers will let you do this. And I will just demonstrate that it doesn't work as it currently is by acting as a non-privileged user. I can try to run my container code, and it complains. It says operation not permitted. Now, it's not that I'm not allowed to fork and exec a program. It's that I'm not allowed to create the namespaces that I was doing. So all this stuff here, I'm not allowed to do as a non-privileged user. But you can add another flag here that says, well, actually, I'm going to use a new user namespace. And I have a little bit of code to save me typing in everything. So what I've got here is I've said, I want to act as user ID 0, group ID 0. That's root. Inside the container, I want to be root. I have to send in some mappings as well to say root inside the container corresponds to, well, whatever my current user ID is, and the same for groups. So the container's view of my user ID will be different from the host's view of my user ID. Now, we'll give this a try, and it will complain again, but this time it's a different complaint. And it turns out that it's line 54 that it's complaining about. And that is where we started doing the mount. So as a non-root user, I'm not allowed to do a mount on the host. But I can get around that by using the namespace for mounts, which are called new NS. That doesn't sound like anything to do with mounts, but apparently it was the first namespace to be added to the kernel. So I guess they thought, new namespace, that'll do. Right, so if we're lucky this time, yes, we're allowed to do it. We've run a container as a non-privileged user, and I can run a shell. Now, interestingly, inside here, I am called root. And we'll do this trick of running a long process inside the container. And we will look for it here from the host point of view. And you can see it's Liz. It's from the host perspective, I'm still Liz, even though inside the container, I'm root. So that's pretty cool. I'm sure Alexa will tell us a lot more about how it actually works tomorrow. It should be great. OK. The next thing I'm going to do is I'm going to talk about C groups, and I need to be root again for this. So C groups is something that, as far as I'm aware, doesn't work yet for rootless containers. And I'm going to want to be back in my folder. Right, so C groups. If namespaces tell us what you can see, or rather what the process can see, then C groups tell us what resources you can use. And they are implemented in a totally different way from namespaces. There's no sort of syscall interface. It's another one of these pseudo file systems. And Vishnu kind of talked about that a bit this morning. I'll show you a bit of how they work. So first of all, let's look at all the different and grep. All the different C groups that are mounted on my machine. There are loads of them. And they cover all these different types of resources that we can have C groups for. So we've got some in here like memory, and some in here like I/O, CPU, and in particular process IDs, which I will come back to shortly. So let's look at memory. And inside the memory directory, we can see a ton of files. These are a combination. Some of these are parameters for the C group, and some of them are sort of stats about what's actually happening. So we might look at the limit in bytes. And this is at the top level for memory, so this is the kind of default C group. And that's a pretty large amount. That's pretty much all the memory on my machine. So by default, processes have no limit. We can see this Docker directory under memory. As Vishnu said, these are hierarchical. So Docker created that, created C groups by creating that directory. And we see, again, the same sort of set of parameters and the same set of stats. This just refers to this Docker C group. And inside that, it's created C groups for each of the containers that I happen to have run on this machine. So creating a C group is just a question of creating one of these directories. So we'll do that. Again, I've got some code that I can copy. I'm going to do the PIDs C group. And I am going to, create my own. So first of all, they're all mounted in this sysfs C group location. Under that, there's this PIDs directory. And what PIDs is a limit on the number of processes you can have running in that C group. I'm going to call my C group Liz. And inside that C group, I'm going to say, we're not going to have more than 20 processes. That's the maximum number of processes I can have in this C group. I'm creating this notify and release file. It just says, if there are no processes left in the C group, you can just delete the C group. And finally, I'm going to write my current process ID. So I'm going to get my current process ID, write it into the cgroup.procs file, and that assigns my process into the C group. I need to make sure I actually call this function, otherwise there'll be precious little effect. Okay. Hopefully I'm now root again, and I can run my container. Okay. And let's check from the VM's point of view, from the host point of view. So there's my Liz directory. And if we look in here, we can see the files that I wrote. I wrote notify and release. I wrote pids.max. We'll just check that. Yep, it's got the limit of 20. I didn't write pids.current. That's a good example of the kernel communicating information through this pseudo file system. Apparently there are 4 processes. Some of those are Go threads. That's a whole other topic. Currently running inside that C group, or currently assigned into that C group. So my container is now constrained to only running 20 processes, which leads me on to this. So you may have seen these. This is a fork bomb, and we're going to check that my container actually is constrained, fingers crossed, touch wood, by running one of these, setting one of these off inside my container. So how this works. We define a function called colon. And in that function, we call colon. And we pipe the results into colon. And we run that in the background. And that's kind of just going to carry on creating processes and eating all the resources in the world. And yeah. We just need to kick it off once. And that's the anatomy of a fork bomb. Let's hope I've typed it in the right place. Okay, so I've set off the fork bomb. We can see very, very quickly that it's not able to find those resources. It can't, fork is failing. And if I look on the host, hopefully, yeah, there they are. There's a bunch of defunct processes, but we're not going to see any more. There's a limit to the number of them, and the reason why there's a limit to them is because of my C group. And I can just check that the current process. Any guesses for what this will show? 20, yeah, exactly. So we've limited the number of processes inside the container to 20, demonstrating the power of C groups, and also, hopefully, how you can write, it's not quite production quality, but you can write a container in, that's 81 lines. Pretty easy, right? Okay, so I've pretty much raced through that so that you're not too late for lunch. The code for approximately that, approximately what I typed in there is available on GitHub, so do feel free to go and experiment with that. Let me know what else you'd like to see. Otherwise, rapturous applause is also welcome. Nice, thank you.